नमस्कार दोस्तों, मैं शिवानंद उपाध्याय आपका स्वागत करता हूं हमारे YouTube चैनल केमिस्ट्री एकेडमी फॉर IIT जेईई एंड नीट। काफी लोग रिक्वेस्ट कर रहे थे कि हमें कुछ जेईई मेंस के लिए करना चाहिए, तो आप लोगों के बीच में हम जेईई मेंस का क्रैश कोर्स लेके आए हैं जो कि फ्री है और इसको हम 32 डेज में पूरा करेंगे। शेड्यूल हमने आप लोगों के बीच में डिस्ट्रीब्यूट कर दिया है, so we'll follow the same schedule. So today I'm going to start with atomic structure. I have divided the atomic structure in two parts. So the first part is very simple. So let us start. तो आइए शुरू करते हैं एटॉमिक स्ट्रक्चर पार्ट 1। सबसे पहले हम कैथोड रेज के बारे में डिस्कस करेंगे, एंड इन कैथोड रेज देयर आर 2 points which are important according to JEE mains. The first point is they are going to ask that what is the origin of cathode rays. So origin of cathode rays is there are two origins. One is the electrode, which is cathode. So the metallic plate, the electrons are emitted from the metallic plate. So cathode is the origin of cathode rays, and the other thing is the gas inside the discharge tube, because when these cathode rays are coming from the metallic plate, they will ionize the gas inside the, or they can excite the gas inside the discharge tube. When they are ionizing the gas inside the discharge tube, the electron will go away from those atoms or gaseous molecule, and we know that cathode rays are made up of electrons. So there are two reasons for cathode rays. One is the metal plate and the other is gas inside the discharge tube. And the second point which is important is a specific charge. When we are talking about a specific charge is always positive. It is magnitude of charge upon mass of the particle. So they can ask the question that alpha particle, an electron or neutron, arrange them in increasing order of specific charge. So for cathode rays, specific charge is fixed because electron is a fundamental particle. If you take electron from anywhere, its mass and its charge is not going to change. So the specific charge of cathode rays is 1.76 into 10 to the power 11 coulomb per kg. This value is also important. It is mentioned, and if you forget, you can find out. You know that what is the charge on electron, 1.6 into 10 to the power minus 19 coulomb, and the mass of electron is 9.1 into 10 to the power 31 kg. So from there you can find out what is the specific charge. The second point is about anode ray experiment, and in anode ray experiment the same points are there. What is origin? So here it is different, because in case of anode rays, the origin is the gas inside the discharge tube. If you change the gas, the anode particle or anode ray is going to change. So origin of anode rays is gas inside the discharge tube, and when we take hydrogen gas, the specific charge of anode rays will be maximum when the gas inside the discharge tube is hydrogen gas. As we change the gas, the mass of gas particle will change and the specific charge will change. So the second point is specific charge is not fixed. It will change with the gas inside the discharge tube. So these 2 points are there, which is related to cathode ray experiment and anode ray experiment. Now coming to the second point. So the second point is related to Rutherford alpha particle scattering experiment, and there are many points in this. The first point is from this experiment, from Rutherford alpha particle experiment, we discovered the nucleus. The discovery of nucleus is related to a Rutherford alpha particle scattering experiment. And the second point is we are doing an experiment when a radioactive substance is there and it is emitting alpha particle, and we are bombarding that alpha particle in thin metal foil. So there are 2 points which is important. Most of the alpha particles will pass through that thin metallic foil, means most of the part of the atom is empty. So they are going to ask that how many particles, alpha particle is going to deflect by some angle, very few of them. So if I am sending 8,000 alpha particle, among 8,000 only one alpha particle will deflect by some angle due to repulsion between the nucleus of the atoms of metal foil. And the second point is among 20,000 alpha particle, only one alpha particle will be returned back. So this 8,000, in 8,000 only one alpha particle will be deflected by some angle, 1 in 20,000 alpha particle is deflected by 180 degree, and from there, this point, third point, we come to know that the size of nucleus is very small, and almost all the mass of the atom is concentrated at the center. Now there is a very common question or doubt of the student that in Bohr's theory we are also saying that electron is moving in a circular orbit, and in Rutherford theory also we are saying that electron is moving in a circular orbit. So why this Rutherford theory fails, right? So at the time of Rutherford there is no development of quantum physics. So classical physics is not able to explain this stability, because according to classical physics, if a charged particle is accelerating, if it is doing circular motion, due to circular motion, it will emit energy, and finally the electron will enter inside the nucleus. So the stability of an atom is not explained by Rutherford, because at that time there is no discovery of quantum physics. So before Bohr's theory, there is some points which we have discovered and proved in quantum physics. The second point, which is very common in JEE Advanced in physics and chemistry, this question is asked many times, that how do we know the size of nucleus? By Rutherford alpha particle scattering experiment, we can find out what is the size of nucleus. So what we are doing here, that we are bombarding alpha particle on thin metal foil, and we are applying the law of conservation of energy. So the initial, because the alpha particle and the thin metal foil is at a large distance, because of that the total energy of the system is only the kinetic energy of alpha particle, because this thin metal foil is stationary. So if metal foil is stationary, there is no kinetic energy. So initially there is only kinetic energy of the alpha particle. When these alpha particle is, when the alpha particle is coming towards the metal foil, due to repulsion between the nuclei of the atom and the alpha particle, it is going to decelerate, and finally it will stop. So when it will stop, there is no kinetic energy of the system. So all the kinetic energy of the system is now converted into potential energy. So we are applying law of conservation of energy. So initial energy of system is equal to final energy of the system. And from there we have calculated what is the size of nucleus. So we are saying that kinetic energy of alpha particle is equal to potential energy of the system. Kinetic energy of alpha particle is half into mass of alpha particle into speed of alpha particle whole square, and potential energy, this K is 1 upon 4 pi epsilon naught. And Z1 into E is the charge on nucleus. The value of Z1 is equal to 2. And this Z2 is related to the charge of metal nucleus on the metal foil. So if it may be gold metal, so Z2 will be 79. If we change that metal plate, the value of Z2 is going to change. So from here we have calculated that what is the minimum distance, and this distance is telling about the size of nucleus. So from this experiment we can calculate what is the size of nucleus. Right, we know that size of atom is of the order of 10 to the power minus 10 meter, while the size of the nucleus is of the order of 10 to the power minus 15 meter. So the size of nucleus, the discovery of nucleus, is related to Rutherford alpha particle scattering experiment. During Rutherford experiment, we are not able to find out that inside the nucleus there is neutron. After the discovery of nucleus, after 20 years, we are able to find out that there is a neutron inside the nucleus, because outside the nucleus the neutron is very unstable. So that is just an information. So this is about alpha particle scattering experiment. Then about Bohr's theory, we know that Bohr's theory, before Bohr's theory we should understand that there are support given by quantum physics. We are discussing about discrete form of orbit angular momentum. We are discussing about discrete form of energy, right? So this Bohr's theory is supported by quantum physics. So in development of Bohr's theory, we know that there are two postulates. Main postulate is that when electron is moving in a stationary orbit, it will neither lose nor gain energy. So this can only be explained on the basis of quantum physics. According to classical physics, it is not possible, because according to classical physics, if it is moving in a circular orbit, it will lose energy and it will enter inside the nucleus. So this is about quantization of energy. We will discuss it later. The second point is orbit angular momentum. So be careful about that. Most of the students are very careless when they are reading about momentum. One is orbit and the other is orbital. Orbital angular momentum is related to Schrodinger wave equation. Orbit angular momentum is related to Bohr's theory. So in orbit angular momentum, we are saying that mvr is equal to nh upon 2 pi. And we know that this orbit angular momentum is moment of linear momentum. You know, by physics, we are saying that position vector into momentum vector, cross multiplication of position vector and momentum vector will give out orbit angular momentum. So we are talking about quantization of orbit angular momentum. We are talking about quantization of energy. So we are applying quantum physics in Bohr's theory. So already I have discussed that there is a difference between orbit angular momentum and orbital angular momentum. Let us move to the next point about Bohr's theory. There are many applications. One of them is expressions for the radius of electron in nth orbit. So we know that radius of electron in nth orbit. I will suggest you that before going to exam, you should remember this formula, because you have to remember this only. I am talking about the expression, not this value that Rn is equal to 0.529 n square upon z. This relation सभी को याद होता है. But I'm not talking about this relation. I'm talking about this expression that Rn is equal to n square h square upon 4 pi square m kz e square. If you don't remember it, I know that you are able to prove, but it will take a lot of time. 2-3 minute तो आपके इसी में लग जाएंगे. So I'm not saying that remember all the things. I'm just suggesting about radius. So radius in nth orbit is equal to n square h square upon 4 pi square m kz e square. अगर ये हमें फॉर्मूला याद होगा तो with the help of that I can derive the expression for speed of electron in nth orbit in single electron system. I can derive the total energy of electron, potential energy of electron, kinetic energy of electron. Other expressions we can derive, but the first expression is about Rn. So Rn is equal to n square h square upon 4 pi square m kz e square. You have to remember it. Okay. So in this 0.529 angstrom is also known as, because you know that in hydrogen atom Z is 1, and when we are talking about the first orbit, then this first radius of first orbit in hydrogen atom is also known as Bohr's orbit. So many times we are using in question Bohr's orbit means the orbit of hydrogen, first orbit of hydrogen atom, that is 0.529 angstrom is the Bohr's orbit. Right. The second expression, now I'm saying that if you remember Rn, then we can derive the velocity of electron in nth orbit. You can derive it by using quantization of orbit angular momentum. We can write mvr is equal to nh upon 2 pi. From here I can write that velocity is equal to nh upon 2 pi mr. And if I put the value of r, and the value of r is n square h square upon 4 pi square m kz e square. So from there we can find out the expression. And in this expression, z and n are variables. Others are constant. 2 pi h k e square. These are constant. So if we put the value of all the constant, we should also remember this value, that is 2.188 into 10 to the power 6 multiplied by z by n. So velocity of electron in nth orbit is equal to 2.188 into 10 to the power 6 multiplied by z by n meter per second. We know that what is the velocity of light. Velocity of light is 3 into 10 to the power 8. So the speed of light is 137 times greater than the speed of the electron in first orbit of hydrogen atom. And we know that as we move away from the nucleus, the speed is going to decrease. As we increase the value of z, like if I compare hydrogen atom and helium plus ion, the speed will be more in the first orbit of helium plus ion than that of hydrogen atom. So these things you already know. I'm just saying that remember that speed is equal to 2.188 into 10 to the power 6 into z by n meter per second, right? So this is about expression for speed in nth orbit. Let us move to energy expressions. So we know that potential energy, because one nucleus is positively charged, electron is negatively charged, the charge on the nucleus is Z into E and the charge on electron is minus E. So potential energy, we know that since the charges are opposite, minus 1 upon 4 pi epsilon naught Q1 Q2 upon R. So in place of 1 upon 4 pi epsilon naught, we are using K. So the value of K is 1 upon 4 pi epsilon naught. So potential energy, we know this is the value of potential energy, and by using the expressions we are able to prove, because when the electron is moving circular motion and neither it is gaining any energy neither losing energy, so we can say that centripetal force is equal to centrifugal force, and by using that we'll prove that kinetic energy is half times of potential energy. So I have used it directly, that kinetic energy is equal to half times of potential energy. Kinetic energy is positive, so all the things are same. Here the sign is going to change, and if I add these two things, we'll get the expression of total energy. So total energy is equal to the magnitude of kinetic energy, but it is half the magnitude of potential energy. And if we right now, if we want to write the expression of potential energy or kinetic energy or total energy, if we remember that Rn is equal to n square h square upon 4 pi square m kz e square, we can derive in few seconds only, right? So here if I want to write that what is total energy, from here I can write that this is minus kz e square upon 2, and I'm putting the value of R. So on putting the value of R, this 2 and 2 will cancel out. So I can say that total energy expression is minus 2 pi square m k square z square e to the power 4 upon n square h square. And all of you remember that, okay, what is this constant? Because total energy is equal to minus 13.6 z square upon n square electron volt per atom. So many of you remember that 1 upon lambda is equal to RH square 1 upon n1 square minus 1 upon n2 square, where RH is known as Rydberg constant, whose value you also remember that value is equal to 109,677 per centimeter, right? So Rydberg constant in your mind is 109,677. If you read NCERT carefully, Rydberg constant is also for energy term. So in terms of energy, when we are writing that the total energy of electron in nth orbit for single electron system is minus 13.6 z square upon n square electron volt per atom, that 13.6 is also Rydberg constant for energy. This thing is given in NCERT. So Rydberg constant is minus 13.6 electron volt per atom. Or if you want to write in terms of joule, you can convert this, right? So don't try to do this in exam, better to remember it, because it will take a lot of time. 13.6, then you'll multiply by 1.6 into 10 to the power minus 19, and then you simplify. Better to remember. This is very common in exam. So 2.188 into 10 to the power minus 18. 2.18 into 10 to the power minus 18. This is the Rydberg constant in terms of joule. And this third value is also mentioned. If you are able to remember it, it is fine. Otherwise, you can leave it. This value in terms of kilocalorie per mole, that is 313.6 kilocalorie per mole. So the main point is Rydberg constant. You understand that Rydberg constant is 109,677 per centimeter. That is correct. But Rydberg constant is also in terms of energy, which we are using 13.6 or 2.18 into 10 to the power minus 18, right? These are also Rydberg constant for energy. And these things are given in NCERT. So when we are discussing about dual nature of electromagnetic radiation, there is a fixed question which is very important for our NCERT and JEE. So we are discussing about dual nature of electromagnetic radiations. There are certain experimental phenomena which supports the wave nature, and there are certain which supports the discrete nature or particle nature. So this discrete and particle nature is important for us. Like when we are talking about wave nature, we are saying that refraction, when the wave will pass through a medium, it will bend, that is refraction. Refraction and diffraction is wave nature of electromagnetic radiations, but photoelectric effect, black body radiations, atomic spectrum, and variation of heat capacity of solid with temperature, Compton effect. There are 5 phenomena which is important, and they are supporting the discrete nature of electromagnetic radiations. If you go through your NCERT, they have discussed about photoelectric effect, they have discussed about atomic spectrum or line spectrum, and black body radiation. So these 3 are very important. Apart from this, these 2 are there in physics, Compton effect and variation of heat capacity of solid as a function of temperature. These all 5 phenomena support the discrete nature of electromagnetic radiations or particle nature of electromagnetic radiations, right? So this is very important, dual nature of electromagnetic radiations. Now, when we are discussing about spectrum, atomic spectrum or line spectrum, this is also known as line spectrum. So I was going through the past JEE mains papers, right? And there are a lot number of questions based on this spectrum. That's why I'm discussing it. So we know that there are 2 type of spectrum, that is absorption spectrum and emission spectrum. We are discussing here emission spectrum. So in case of emission spectrum, when we are saying that Lyman series means the electron, we are discussing in single electron system, the electron is moving from higher orbit to the first orbit. So when the electron is moving from higher to first, it will emit energy in the form of photon. And we know that the wave number of that photon 1 upon lambda is equal to RHZ square 1 upon n1 square minus 1 upon n2 square. And we know that what is the value of Rydberg constant, right? So be careful that its unit is in meter or centimeter. In centimeter, it is 109,677 per centimeter, but in meter, it is 109,67700 per meter. So we know that for Lyman series, N1 is equal to 1. Now, for hydrogen atom, if we are talking about Lyman series lies in ultraviolet range. So first thing is that in NCERT, they have given the spectrum, right, of different electromagnetic radiations. So we should know that what is the increasing order of wavelength or increasing order of frequency of those electromagnetic radiations, means we are talking about photon. So this is the increasing order of wavelength. So the first one is gamma radiation, then X-ray, then ultraviolet, visible range, infrared, microwave, and radio wave. So this order is very important, and especially when we are discussing this, visible range is very important. So if we follow NCERT, in visible range, they have given a range of wavelength. We should remember that wavelength given in NCERT, that is for 4,000 angstrom to 7,500 angstrom, because in different books the values are different, but we have to follow NCERT. So 4,000 to 7,500 angstrom, that is visible range, because sometimes in the question they will give the value 5,000 and they will not mention which series. So you should know this value 4,000 to 7,500 in order to know that that is Balmer series. So when we are talking about Balmer series, the electron is moving from any higher orbit to the second orbit. So in this also, when we are framing the questions, we are saying first line, second line, last line. So the first line means it is moving from the third orbit to the second orbit in Balmer series. So it is the minimum energy difference for Balmer series, third orbit to second orbit. So we know that energy for a photon E is equal to hc upon lambda. If energy will be more, the wavelength will be less. So what is happening that when we are moving from third to second, that is the first line, the wavelength of the first line is maximum. And Balmer is in visible range, so we'll say that it is towards the red color, right? So when they are saying that last corner of red color means they are talking about, in BOHR'S series, they are talking about the first line, right? And we know that VIBGYOR, so red color has maximum wavelength, the violet color has minimum wavelength. So that is important, that when we are saying, most of the students remember that what is the range of wavelength, but how many of you remember what is the range of frequency? Because we know that for photon, C is equal to nu into lambda. We remember the range, right? If you forget, then you can apply the formula. C upon lambda will give you the frequency. So the order of frequency, you should know order of frequency for visible range if we discuss here. So I think that value is in the next page. We'll write it. We'll discuss that point. Right. So here what we are discussing, that 1 upon lambda is equal to 10967700. It is in per meter, 1 upon n1 square minus 1 upon n2 square. So this energy of photon, because we know that energy of photon can be written as hc upon lambda, or it can be written as h into nu. So this formula is also important. The frequency of photon, none of you will remember this frequency, this data, because everyone has remember 109677. This is given in NCERT, right? So you should remember, because it will take a lot of time if you try to solve it, right? So better to remember this. 3.29 into 10 to the power 15. So order is 10 to the power 15. 3.29 into 10 to the power 15. 1 upon n1 square minus 1 upon n2 square. So this is something which is given in NCERT, but nobody cares about it. And if the question will come, everybody will say that question is easy, but it will take a lot of time to convert and get this value. That is 3.29 into 10 to the power 15. So be careful about this, right? So let us move further. So what I was talking, that in visible range for BOHR'S series, the value of wavelength given in NCERT is 4000 angstrom to 7500 angstrom. And if I convert into frequency, right, you should remember this value. You can convert it. If you forget, there is no point here to discuss, but yes, C upon lambda is frequency. So that value is equal to 7.5 into 10 to the power 14 to 4 into 10 to the power 14, right? So this range you can find out. There is no problem in that. I'm not saying that remember the frequency, remember the wavelength, right? So when we are talking about BOHR'S series, when the electron is moving from third orbit to second orbit, the energy difference is minimum. So corresponding to this, wavelength is maximum. So when they are saying longest wavelength of BOHR'S series, so they are talking about the first line. When they are saying that shortest wavelength of BOHR'S series, they are saying that electron is moving from infinity to the second orbit. So largest this difference, right, from infinity to the second orbit, then we'll say that it is shortest wavelength. So shortest and longest wavelength, be careful about that. And in NCERT, they have mentioned that in BOHR'S series, the first line is red in color, the second line is green in color, the third line is blue in color, the fourth line is violet in color. Since it is mentioned, that's why I'm discussing here that you should also know that first four line colors are given in NCERT. So red, green, blue, and violet. In past years, there is a question, very good question asked regarding this atomic spectrum, and I'm discussing here what is happening, that when we are saying that we know that in single electron system, as we move away from the nucleus, the energy difference between the consecutive energy labels are going to decrease. So we'll say that the highest energy gap is between first to second, then second to third, it is less than first to second, and so on. As we move away, the energy difference between consecutive energy labels are going to decrease. So based on that, in JEE Mains, there is a very good question asked. And the point regarding to that question is, as the wavelength decreases, the lines in the series converge. So when we are talking about that, when we are moving from higher energy level to the second orbit, as we move away, when we are increasing the value of n, so if I am saying that the electron is moving from sixth orbit to second orbit, then I will say that electron will move from 7 to second orbit or 8 to second orbit. As 6, 7, 8, these photons, the energy difference between these photons are going to decrease, because we know that as we move away, the energy difference between, so we are saying that the energy difference between these photons are going to decrease, means these photons are converging. The wavelength difference is also less, so that's why this word is used here. As the wavelength decreases means we are discussing, we are going from higher to the second orbit, right? So as the wavelength decreases, the line in the series converges. So this word is important. I have told you that what is the meaning of converge. I hope that you understand that what is the meaning of converge. So this point is asked in I think 2-3 years back. This point was there in one option. Okay, so this is about the spectral lines. Let us move further. Okay, so de-Broglie equation. So we know that de-Broglie equation, we are talking about dual nature of photon, and we are talking about dual nature of electron or atom or molecule, subatomic particles. So lambda is equal to h upon p. Now if I differentiate, because we know that wavelength and linear momentum is inversely proportional, if I differentiate both sides, I can write that d lambda is equal to minus times of h upon p square into dp. So this d lambda is uncertainty in wavelength, and this dp will be uncertainty in linear momentum. So why we are discussing this? Because when we are going to solve questions of Heisenberg uncertainty principle, sometimes they will ask that what is the uncertainty in wavelength. So we know that Heisenberg uncertainty principle is delta x into delta p is equal to h upon 4 pi. So there the value of delta p, we have to eliminate that delta p and we have to write the value of delta p in terms of delta lambda. So there one application, all the good questions of Heisenberg uncertainty principle will apply this concept. So be careful about that. The second point, which is very important, when we are saying that relation between kinetic energy and linear momentum of a particle. So we know that kinetic energy can be written as p square upon 2m. From there we can write that linear momentum is equal to under root 2 times of mass of the particle into kinetic energy of the particle. Now if this particle is a charged particle and it is accelerated in electric field, and initially the particle was stationary, then the kinetic energy gained by the particle is equal to Q into potential difference applied. So in place of kinetic energy, we have written that kinetic energy is equal to Q into V. And since we are assuming kinetic energy as positive, so we have taken the positive sign of Q, and then we are saying that Q into V is kinetic energy. So linear momentum, now I can write that under root of 2 into m into Q into V. If I place this value of linear momentum in the formula, I can write that lambda is equal to h upon under root 2mq into v. And if this charge particle is electron, we know that mass of electron and charge on electron, Planck constant. If we put all these values, this value is equal to under root 150 divided by v, where v is volt applied to accelerate that electron. So this is valid only for electron. If the charge particle will change, this formula will change. So be careful about that when you are applying, because this is this very common formula. So when we are applying this formula, this is also given in physics, lambda is equal to under root 150 divided by v, where v is in volt. This is only valid for electron. So suppose in place of electron, some proton is there. So you will apply this formula and then you can relate and solve it. This is first thing. The second common error when we apply this formula, right? So same type of formula is there for photon. So when we are talking about photon, we are writing that wavelength of the photon is equal to 1240 divided by energy of photon in electron volt. Energy of photon is in electron volt, and this is approximate value, right? So similar type of formula is there, right? Here also wavelength and here also wavelength. but be careful, you intermix this formula. This formula is valid for photon. Energy of photon is equal to, it is approximately equals to 1240 divided by energy in electron volt, right? So don't confuse, this is for electron and that is for photon. आगे बढ़ते हैं क्या मिलता है देखते हैं. So next is quantization of orbit angular momentum, because Bohr's was saying that orbit angular momentum is quantized, but he was not able to explain. In order to explain this, we are using dual nature of electron, right? When de-Broglie equation, we know we are able to prove that y mvr is equal to nh upon 2 pi. So they are discussing the same thing. According to de-Broglie equation, lambda is equal to h upon mv, and we know that if this electron is behaving like a stationary wave, for a stationary wave the position of maxima and minima will be same, and that can be possible when this whole path is integral multiple of lambda. So for a stationary wave, the positions of minima and maxima is not going to change, and that can be possible when this path is integral multiple of lambda. So using that concept of a stationary wave, we are saying that the path 2 pi r should be integral multiple of lambda. So in this equation, first equation, there is no lambda. So we are putting the value of lambda in this equation. So from there, we are able to prove that mvr is equal to nh upon 2 pi. So there are questions based on this concept of a stationary wave. Like when we are talking about the third orbit, because the number of waves in a particular orbit is equal to the orbit number. If I am saying that third orbit, the number of stationary waves in the third orbit is equal to 3. Fourth orbit, number of waves is equal to 4. So using that concept, if I am saying that in the third orbit, the value of R3, since it is a single electron system, so Rn value is equal to 0.529 n square by z angstrom. So 0.529 means Bohr's orbit. So Bohr's orbit A naught n square by z. So if for hydrogen atom, if I am calculating that, what is the value of third orbit? So n is equal to 3, z is equal to 1. Third orbit is 9 times of the Bohr's radius, right? So R3 is equal to 9 times of A naught. And we know that 2 pi r is equal to n lambda. The value of n is equal to 3, and we want to calculate lambda in terms of Bohr's radius. So from here, we can calculate that. So this concept is used in many questions, right? That path difference is integral multiple of lambda. So the point is, in nth orbit, the number of waves is equal to the orbit number. Heisenberg uncertainty principle. I was going through past year questions. There are many questions which is based on this, so I have to discuss. Like we know that uncertainty in position and uncertainty in momentum should be greater than equal to h upon 4 pi. So the first point here is that if I divide and multiplied by dt, time, right, uncertainty in time in numerator and denominator, if we write, rate of change of momentum with respect to time is force. So dp upon dt is related to force. Force into displacement is work, so it is energy. So delta x dot delta p upon delta t, this is delta e. So delta e into delta t is greater than equal to h upon 4 pi. This is another form of Heisenberg uncertainty principle, which is uncertainty in energy into uncertainty in time is greater than equal to h upon 4 pi. This is the first point about Heisenberg uncertainty principle. The second point is, when we are finding the uncertainty in position and uncertainty in momentum, they should be in the same direction. If I am finding the uncertainty in position in x direction, I am also finding the uncertainty in momentum in x direction only. I cannot find in y direction. So both uncertainty in the same direction. And the third point, we should have a feeling like when we are doing physics, we are using that vernier calipers, we are finding out least count of an instrument, right? So when we are using a scale to measure a distance, in our scale, whatever we are using, 1 millimeter is the least count. So when we are sincerely doing an experiment, what we can do an error, human error, that suppose I have to read 10 millimeter. In place of that, I can, if I'm doing sincerely also, it may possible that due to human error, that in place of 9, I can read 8, or in place of 9, I can read 10. So whenever we are doing error in terms of the least count. So here, this point is very important. Delta X uncertainty in position should not be greater than position. So first thing is that when we are doing error in terms of least count. And the second thing is that whatever the value of least count, suppose if I want to measure a distance, if the distance is less than 1 millimeter and I have a scale whose least count is 1 millimeter, then I cannot measure a distance which is less than 1 millimeter. So that is the point, that uncertainty in position should not be greater than position itself, or uncertainty in momentum should not be greater than momentum. So the maximum value of uncertainty is equal to the position. Delta X is equal to X, that is the maximum value, or delta P is equal to P, that is the maximum value. Delta P cannot exceed P, delta X cannot exceed X. So uncertainty is related to least count of the measuring scale. And all the good questions of Heisenberg uncertainty principle, when they are discussing, they are using De-Broglie equation, that lambda is equal to H upon P. By differentiating De-Broglie equation, we can say that uncertainty in wavelength is related to uncertainty in momentum, and that we can use in Heisenberg uncertainty principle. So in good question, we should not forget about this relation. Whenever they are saying about uncertainty in wavelength, means they are using Heisenberg's uncertainty principle along with De-Broglie equation. So in the second part of atomic structure, we are going to discuss about Schrodinger wave equation and its application. Many questions on quantum theory, Schrodinger wave equations, right, has been asked in JEE Mains in current year. So we are going to discuss that part. Thank you.